try to work in this area. And so she made a lot of mistakes. You need somebody with a more physical chemistry training or electrochemistry training. And I mean, she tried. I give her credit for trying. And some people who were supposed to help her, like Pat Hagens, he thought it would ruin his career to get involved, so he just tried to stay away as much as he could, not even help her. You know, even though he was supposed to help her out. And so a lot of the money went to NRL, but they did not have the right people working on it, and they never got anything positive. I went there towards the end of the program to help Don work on it. And I did about 3 weeks working at NRL, staying in a motel there on the other side of Washington D.C. And she had this new calorimetry that was called a CBEC calorimetry, and she'd been getting. She had a stack of data like this high. And the person that made the calorimetry came in to look through it and help her analyze it. And I went to dinner with him one night, and he said, "You know what? That entire data, all that data is useless." He said she never made it. She never measured where the 0 point was. So I have no way of knowing what that shows. It was 3 months of data, just pile of paper that he was supposed to help analyze. And I don't think he ever told her that, but he told me that it was just all useless. She hadn't done it right, and that wasn't really her training. I don't blame her too much, because organic chemistry is quite different than physical chemistry. And but I mean, it was just too bad they had the wrong people working at NRL at that time. She later came in and worked with with Kidwell and these other people, and she's been to some of the meetings, like she was there in India, meeting in India, and gave a presentation. But it's just too bad what happened to NRL.
When you look at what the Pons and Fleischmann experiment looked like, it did look simple. I mean, it looks like, yeah, let's put one together.
Right, yeah.
But that's deceiving, isn't it?
Very deceiving, because there has to be certain conditions you have to do to make it work, and even those will fail if you don't have a good batch of palladium. If you don't, there's some unknown factor in the palladium that we don't understand. Like some palladium works and others doesn't. Of course, according to mercury, it depends on whether it can load to a high level. Not all palladium can do that, but what makes it so some can load high and others do not, and we don't understand the reason why. And Martin Fleischmann has told me several times. He said that it'll take another Manhattan Project to really understand this. You know, like for the atomic bomb. I mean, there's so many things like metallurgy and the palladium and just a lot of things that we don't know yet. That was his opinion of all the work that he did, and still not having a definite answer at the end on how to make it work every time.
What year was that? That Don was doing this?
This Navy, this article kind of talks about the Navy program, but it started after the second conference in Como. Como was June, July 1991, and we come back after that because that conference, the Navy made quite an impact. I presented that helium-4 was a product, and Stan Spock presented co-deposition. It was another method to use to get good results. And Bob Nowak was there. He's the Navy funding officer for electrochemistry. And when he came back, he talked to people. I talked to Fred Suppleton. He had a lot of opposition at ONR, but
you like that ragtime, huh?
Yeah. Well, no, I'd rather have a real telephone ring, but I couldn't figure out how to do that. Even had my son look at it, he couldn't figure it out. So
No, they don't put that on there all the time.
they don't, right?
You
Yeah.
have to download it.
Right, yeah, right, yeah. But the Navy program was finally got underway in 1992. So from 1992 to from about January 1992 to about July 1995, that was the Navy program for San Diego, China Lake, and NRL. And
Everybody got funding.
right, everybody got some funding. And but San Diego didn't get as much because they were getting funding from Frank Gordon. He was helping them out. And so I guess most of the funding went to China Lake, and NRL got a lot more than I did. But they got nothing to show for it, basically. And I got in trouble for putting that into my report. Did I give that to you yesterday, or
What report?
the Navy report at China Lake? Or-
The
I don't know.
effects in deuterated systems. You showed it to me.
Oh, yeah.
I think it's over there in this
Okay.
pile.
Maybe I put that here.
Actually, is this right there?
Oh, okay. Do you have trouble keeping track of papers?
Yes.
In my report, I made mention of that. Well, like right here, I say, this is toward the very end of the report. Some comments are necessary concerning the major disappointment that no excess power was measured in experiments conducted at NRL. So I kind of took on NRL. And during the last year of the program, very sensitive CBAC calorimetry was placed in operation at NRL. Due to various problems, no valid experiments was completed. I said, no valid experiment was completed. That's okay. I thought were completed. Using the new calorimetry. In conclusion, the calorimetric effort at NRL was indeterminate. No excess power was detected, but there were also no calorimetric experiments completed that were capable of measuring the level of excess power obtained at China Lake. Thus, the ratio of excess heat produced in experiments at NRL to the number of valid experiments capable of detecting excess power level of 1 watt per cubic centimeter, that's what I use, was 0/0. No valid experiments, none showed excess heat, and there's no valid experiments, or indeterminate. 0/0 is indeterminate number. They got 0 out of 0. And that made a lot of people
This
angry.
report came out at the end of your funding.
Yeah, you're right. My funding ended in 1995, and I wasn't. They weren't even allowing me to write a report until Dave Nagel gave them the money. It was only because of Dave Nagel that this was ever written. China Lake wasn't going to support it by writing a report. But when Dave Nagel provided the money, then they said okay.
So the funding had ended before this report.
Yeah, before I even started writing this report, the funding had ended. And therefore, to be writing this report, I'd be doing it without any funding, and they said I couldn't do that. And so Dave Nagel kind of saved this, just not ever being written. And so I spent several months writing this report with funding, my time paid for by Dave Nagel.
Was the San Diego group still getting funding at that time?
Yeah, they continued to get funding from Frank Gordon through all these years. You know, up to the time that Frank Gordon retired, he made sure they had some funding all the time. So if you have somebody high up like Frank Gordon, then you can keep working. But I never had that at China Lake. They only tolerated if I had funding. But,
The NRL they're still involved in this, though. For
Right.
instance, David Kidwell was at
Right.
ICCF 18.
Right.
How is it that they're still involved if they felt it was the
Yeah.
end?
Well,
Why did they still stay involved after?
well, their funding ended too, but later on, Bill Wilson at DITRA, Defense Threat Reduction Agency, got interested in funding, and you know that's I think Defense Threat Reduction Agency. I don't know whether that's Navy or what, but you know NRL.
DOD.
What?
DOD, I think.
Yeah, DOD, right. And he was supportive of this field, and he wanted to find out whether it was correct or not. And NRL has a very good reputation, so they naturally want people at NRL to do it. You know, NRL has a much better reputation than does China Lake for research. It is the Navy's research laboratory. It's a naval research laboratory. That we even had a research department bothered some people at NRL. Why would we have a research department in China Lake when they were supposed to be the research laboratory at Washington, D.C.? So you see the politics there. And we were the only Navy laboratory at China Lake that had a research department. Nobody else did. We were just supposed to be programs, work on programs, you know, missile programs of different kind, and not really doing basic research. That's supposed to be at NRL. So Dave Nagel even talked at one time maybe making China Lake Research Department a part of NRL. That would have been a good idea probably. Then we could have we'd be part of NRL, but we could be at China Lake and do research there at China Lake. But that never happened. I thought that was a good idea at the time. But anyway, when Bill Wilson wanted to fund this again, and this happened around 2005, Mike Mealy got a meeting at San Diego with Stan Spock and Pam Boss, and had me come down, and people from Los Alamos were there, and Bill Wilson was there from DITRA, and we all gave presentations, and Bill Wilson got convinced that this area should have to take another look at this area, but he wanted mostly to fund NRL. I eventually got 1 year funding out of it, but that's the last time I actually saw Stan Spock. He was getting pretty old, and I remember when he got up to give his, you know, using view graphs. That's what most people still use. I think we still use view graphs back then, but his hands were like this, you know, and trying to get a view graph. I kind of feel sorry for him, but that's the last time I've seen him. I think he's still.
He was probably happy to be there.
Yeah.
Be part of it.
Yeah, right. And but he's always a good friend of mine. I'd known him for years before. In 1967, I went to work for the Navy in Corona, Naval Ordnance Laboratory, Corona. That's near Riverside, or if you know that area.
Not real well now.
Right, yeah. San Bernardino.
I mean where it is.
Yeah, right. And so I worked there, and Stan, after I'd been there about a year, Stan came to work there, so we worked together for a while at a Navy laboratory. So I knew him clear back from 1967, 68. He was not married at the time. He got married later. I remember he wanted me to he liked track and field. I went to the Coliseum in LA to went with him on a track and field, big track and field event, you know. Really good. But later he met somebody from another country, and he got married. I've never met her, but when I called Stan on the phone, she answered the phone, and it's kind of hard to understand her because she's from, I think, Eastern Europe or somewhere. But of course, Stan is from Poland. He was born in Poland, and so he's from Eastern Europe himself. And Spock, that's the Polish name, S-C-P-A-K.
Well, let me get this full story, because you had some funding from 92 to 95, and you had gotten positive results finally by the end of 1989.
Right.
Were you continuing to do work from 1989 till you got like official funding in 1992?
Yeah, because you know, Bob Nowak he was involved before this was ever announced. He was funding Fleischmann and Pons, Office of Naval Research. so he knew about this work a couple years before it ever surfaced publicly, and but he encouraged them to try to get money from DOD, not just ONR, and they sent in a proposal, and it was sent out for review by Steve Jones of BYU, and that's where Steve Jones got into the picture. Well, Steve Jones, even though he's a member of my church, which is Mormon Church, and I went to BYU. I went to BYU, and then I went to the University of Utah. But he's a shady character. I can put it that way. and so when he read that report, he'd done a little bit. You know, he's thinking that tritium appearing in around volcanoes was maybe due to fusion in the earth. So he had a concept there was fusion going on in the earth, and he claims to, after he read the proposal, he claimed to have done experiments clear back in 1987, 86 on this. He tried to claim priority with his own experiments, even though they were very crude if he did any. He might have written down things in notebooks that he quotes. He thought about it, but he really got back into doing it when he read their proposal, and he was looking for neutrons, and he wanted to present a paper on this, and before Fleischmann and Pons really wanted to even make this known. So that forced Fleischmann and Pons and the University of Utah to make this announcement that they'd been doing this work, prior to Steve Jones. But that's because the whole problem was Steve Jones wanting to present it and claim it as his own work. I mean, at least the neutron part. And
so Bob Novak, who knew about this research prior to the announcement,
right,
and is your boss,
right,
he just kind of slid you a little bit of extra funding from the general budget here and there.
Yeah. At that time, I had 2 postdocs working with me, or maybe even, I think it was 2. I think at one point I had 3, but that's most I ever had. And he told me that I could work on it on the back burner. He said, he didn't want me to neglect what he had funded me on, but he said, you can go ahead and work on this on the side, And one of my postdocs got very interested in this when it was announced. That's David Stilwell. He's on some of the papers, and he wanted to work on it full time, which is fine with me. The postdoc is kind of free to do what he wanted. So he and I spent a lot of time developing the calorimetry together. He'd come up with ideas, I'd come up with ideas, and we finally got to the point that we could at least break even. Usually we're getting less heat out than we put in, and that's not possible. So we kind of worked up where we could break even. And then we knew we had the calorimetry was working fairly well. And our first paper was presented at the Santa Fe meeting in May or June of 1989. By then we were able to show that for both water and heavy water, our heat out to heat in was 1.0 plus or minus 0.04. 1.00 plus or minus 0.04. The ratio of heat out to heat in. So we were getting a good balance on both heavy water and light water. And we presented that at the meeting, and it got published later in a journal publication called Journal of Fusion Energy, I think. And DOE was calling me because they knew I was working on it, and I was reporting we'd got it exactly break even, and all the way till September. That's the best we did. We could just get the heat out that we put in. And so when the infamous DOE report in November of 1989, if you look in there, Miles and China Lake is listed with Caltech and MIT as groups that did not find excess heat. And I didn't find it until September. But I told them in September I seen excess heat, but they didn't want to hear that, I guess. So they never changed the story. And so they just published that I was in the negative group.
So it really took you, April, May, June, July, August, September, 6 months
Yeah,
to really get the calorimetry to the point where you knew what you were seeing and you knew what you were going to be able to measure.
Right, yeah. It took me, by then, Caltech had got in, got out. Within 2 months, they jumped in and said there's nothing here and rolled over paper and they were out. But there were so many variables. How can you test the variables at that time? There's the current density. What current density do you use? What current density for loading? What current density later on? How to configure the cell, the geometry of the anode and cathode. All sorts of variables. The heavy water, how pure does it have to be? And all these different things. There's different types of electrodes. I was even thinking of alloys by then. It'd take a lot of time to investigate palladium silver. I never even wound up, well, I guess NRL did make some palladium silver and I did finally test it eventually. But then there's titanium and there's other metals that could absorb hydrogen. It was just I could see it's just too big a field to even to know that you're doing the experiments the correct way, like even how long to run the experiments. Hardly anybody knew that it might take 2 or 3 weeks for the effect to show up. You can't just turn it on, run it for 2 days, and say nothing's there. If I did that, probably every experiment would have been nothing, no excess heat. I don't ever recall palladium ever showing excess heat unless you did the experiment for at least a week before it would show up. And so these things were not known. And so how could Caltech? They threw a lot of people at the field. They're on their paper, there's I think 20 people listed as authors on their publication. So they just threw a lot of people at it in a very short time, and they tried to do calorimetry. They didn't even know how to develop calorimetry. They did a very poor job. But that's the one thing I do understand, was very poor calorimetry they used. But they also tried to measure helium-4. But if you're not getting excess heat, how can there be helium-4? You don't get excess heat, you don't see helium-4. And besides that, their detection limit was 1 part per million for helium-4. Well, if you do a calculation for the excess heat you're getting for the gas coming off, it'll be in the parts per billion range, not parts per million. So that they wouldn't have been sensitive enough to see helium-4 even if it hadn't been produced. There's so many things I could find wrong with what they did. And
How many cells did you have going at that time? During that 6 months?
I always had two. I had 2 cells going most of that time. I had 1 water bath, and I had 2 cells, and the cells were not nearly as good as they were later, but they were in a plastic bottle with insulation with insulation inside. Then a large glass tube inside the insulation, and then my cell was actually inside that larger glass tube. And I measured the temperature. The larger glass tube I filled with water, so I didn't measure the temperature right in the cell. I measured in the water surrounding the cell, and that way the liquid level. We had a real problem because with our small cell, the liquid level was falling down quite fast, so our cell constant was going like this downhill, and so it was changing too rapidly. So when we put the thermistor in the outer cell, then that smoothed it out, and the cell constant just changes gradually. Mm-hmm. So we could do better work that way. But,
and how did you first discover, in September 1989, I've got, it worked. I got excess heat. I'm seeing something. How much heat was it, and how did you first see that?
Before, everything was just kind of bouncing around 0 because there's experimental error, plus or minus 4% of 0. Mm-hmm. 1.04 or 0.96. I was measuring heat, the ratio of heat out to heat in. That's the way I was doing it. And it was bouncing around 0, plus or minus 4%. And then when and the palladium I was using, I keep using the same palladium because that's all we had. And I later, a couple years later, I found out that palladium did not load very well at all. So it would have never probably given excess heat. So it was only when I got the new Johnson Matthey shipment, which was the 6mm rod, that I cut 2 electrodes about that long. From the rod was about this long. I cut 2 sections like this, and it's kind of like the thickness of a pencil, and attached the leads and put those in, and it still stayed about 0 for about a week, and it started going up. It never went to 0 again. It just stayed up in this other range, and it was around up to about 30% excess heat. And my air was plus or minus 4%, so what's that, 7, 8 standard deviations, which is very significant. It was staying up there at this about 30% excess heat.
So just about immediately when you got this new material, you set it up, and a week later, after a week of the loading, you saw it.
Yeah, right.
What did the people in your office say at that time? Like, yay?
I don't know. You know, I'm kind of private. I guess maybe I never even announced it. I mean, well, let's see. David Stilwell and I guess we were pretty excited, and I think I reported it to my branch head at the time, but I didn't go beyond there. You know, but you know, they look at it and they say, well, how do you know that's the 0 isn't up here? You know, they without knowing the calorimetry. I've had people come in and they see my graph and they see the exceed up here. So what if the 0 line is up here? You're just seeing errors, you know. So if you don't
As if you
understand the
didn't take that
calorimetry,
into account.
yeah, if you don't understand the calorimetry, they don't really appreciate it. But after months of seeing 0 plus or minus 4%, I appreciated the fact this was very different. Mm-hmm. But not everybody would have done that. Mm-hmm. I mean, because you don't visually see anything, except what you measure and calculate comes out different. And so those are, David Stilwell, I think his postdoc ended and he left about that time, but he's still in a lot of my early papers because I give him about equal credit for his work on developing calorimetry. Because he did a lot. We tried all sorts of things that didn't work well, but
where is he now?
He actually, when he left me, he got a 1-year appointment at Southern Oregon University. He got up in Ashland for the first year, but he didn't get He didn't get on permanently, and that was let's see, that was about 1990, I guess. You know, probably the fall of 1989 through the school year 1990. That was the year he was up here. Because I remember, because I came up that winter to plant, that's when I first started planting the trees. Well, David Stilwell helped me plant the first few trees. He worked the first day up here with me, and my 2 kids. So some of the trees on this very corner, plus the cabin, that's where we started. Some of those were planted by David Stilwell, actually. And, but he didn't get a current position, so he wound up getting a job in the state of Connecticut. I think he's still there, maybe. In a state laboratory where they analyze water and different things. He was an analytical chemist, basically.
He's not in the field, though.
No, I've never heard from him since. I included his name on my Journal of Physical Chemistry publication because he had a lot of help in that early calorimetry. It was my name in Kwang Park. He was born in Korea and then became a U.S. citizen and got a PhD at the UCLA, and then came to work with me as a postdoc. And so Kwang Park and David Stilwell and myself were the authors on that paper.
So you found this finally 6 months after the calorimetry. You're getting maybe 30% excess heat. And what happened then? what did you decide to do next after you saw it?
Okay, the very next thing I ran it as long as I thought it was just staying next to the seat. I decided to turn it off and just try it again. So I turned it off and cleaned everything up. I repolished the electrodes and I set it up again, and I ran it again and I got excess heat again. And I ran it longer. It was not as large excess heat, so here I was repeating this, using the same electrodes the second time, which Martin said he never really looked at that, but that's an important point. And I even ran them a third time, and that ran through the winter of that year. This was 1989 still. I guess I turned it off when I came up here to plant trees, probably. You can't run it there all the time. But so I ran it 3 separate times, and maybe a month or 2 each time, and it gave excess heat every time. And so that was the paper I reported at ICCF 1 in Salt Lake City in 1990. That was where Stan Pons came over and congratulated me, where I first met him and shook hands with him. Because during one experiment we had a power failure, and so it deloaded the power, and when it started up, it was back to 0 again. Well, that was a good thing that happened, because it showed you that once it deloaded, it went back to 0, and then it started up again, and then it started going up again, excess power. And that's a good thing that shows you your 0 is still there, because it was accidental, but it was good to have that happen. And
So into 1990, you were just repeating this, and you still had that same palladium material that was working
right.
through 1990.
Right, yeah. And let's see, that was reported at the first conference. So I had excess heat before the DOE published their report. I had it in September of 1989. That's when I first had it. And I had it all through the fall, and I don't remember. I'd have to go, I still have all my notebooks from that time. Because, the Navy's supposed to keep your notebooks, but I thought this could be important, and I didn't like the style of their notebooks, so I went and bought my own, and I had never registered them with the Navy, and so I still have those notebooks. The Navy would eventually thrown them out, but I thought it was important enough I should keep them. So I have all the notebooks of all this time period where I did experiments.
And at this time, you didn't have any postdocs, though.
Well, David Stilwell left, but I still had Kwong Park, and so he continued to work with me until his postdoc expired. And then there was a period I didn't have any postdoc, and then that later led me to think about doing helium-4, and that was getting into later in 1990. Ben Bush called from the University of Texas, wanted to know if he could do a postdoc with me, and we got talking about helium-4. China Lake did not have the instrument that was capable of measuring helium-4 like I wanted, and he said they had it at the University of Texas. So we decided to collaborate and collect samples, and I would ship them to him. And that was the first paper on helium-4. I used the same 2 electrodes again. They were giving me excess heat every time. And when I did that helium-4 experiment, I got large effects, about as large as I ever saw at any time, up to up in the high 30% excess heat. It was sometimes it's lower, sometimes it's higher, and when we had no excess heat early in the experiment, then Bush found no helium-4, and I didn't tell him which was which. I collected the flasks, but I just coded them with dates of my kids' birthdays and so on, and I never told him which were which, because I didn't know anything about him. I want to make sure, and I learned later that was good, because Ben Bush was the type that he was convinced was real, and he would tweak data to make it real if he had to. I wouldn't trust him. if I hadn't if I told him which were which, I would not really trust what he did, perhaps, because he was too zealous that this had to be correct. and you probably, I don't know if you met people like that, but they want the experiments to be the way they want them, and they'll fit around with it till it's that way. And I'm never that way. I just like to report whatever I get.
So you basically perform the experiments in your lab,
Right.
collecting the released gases,
Right.
and then you took those collections of gases and mailed them to his lab where he did the analysis of that gas.
Yeah, we did a one-day shipment, UPS or something. And one problem I have with Ben Bush later in Charles Boudet book, he's talked to Charles apparently, and he tries to take too much credit. But all he did was measure the helium-4. But I had people at China Lake that I didn't know they let me publish it at China Lake. So I let them publish the paper and be the first authors on it, even though his supervisor Legowski did hardly nothing. Ben Bush did and he didn't even do the helium-4. He just had a person there at the University of Texas analyze it, and but they got their names appear first on that first paper, and sometimes he gets a lot more credit than he should have. Because I did everything experimentally except to measure the helium-4. But Ben Bush was an expert on keeping air out, and I would say I could not have done it without Ben Bush probably, because he knew how to keep air out, and we discussed how to flush the flask. We had the flask connected to the line all the time, but before we'd collect a sample, we would take the boil-off nitrogen, which is supplied right into the lab, and pass it, flush it out through the whole system. So any helium from air would not be there, because boil-off nitrogen does not have any helium in it, because helium boils much lower temperature, so it would be long gone before the nitrogen would boil off. So this big huge tank of liquid nitrogen, the very top is the gas that's in there, and this is what they call the boil-off nitrogen, and there's no helium in it at all. And we flush the system out. It comes through metal lines right into my lab, and I would connect it to the whole system. It would flow through the whole system, and it would go out through an oil bubbler. That is, it doesn't bubble into the air. It bubbles through an oil so that no air can get back in. It forms bubbles in the oil and it comes back up, and the air can't backflow into it. And so this is why I do this at night. It had to be all done very precisely. And everybody at China Lake always said I was about the most careful of any scientist. And I was so careful I would come in where nobody could disturb me and do this when I had to do something critical like that, or on a Saturday. And I'd even shut the door and lock it so nobody, even if they were there, couldn't bother me during that period. So we'd flow the nitrogen through for maybe 10-20 minutes to flush it out. Then I would close off the nitrogen, and then the cell was producing excess heat. So I would let it flow through I let these gases coming off flow through the system and through the oil bubbler, and you can see the bubbles coming through the oil bubbler. Just bubble, just about every second there'd be a bubble that disengage and flow up. That'd be the deuterium and oxygen gases being produced, and I would wait a good several hours. So this took quite a bit of time to just collect a sample, because after flushing it, you'd have to let it flow through the system for a period of time where you're measuring the excess power. So you knew the excess power during that time span, and you made sure that all the gases came from your cell, and they were bubbling through the cell and through the oil bubbler, and then you just shut off the valve and still the flask, and then get it ready for mark it with some code and get it ready for shipment. And so that was the way that the gas samples were collected. But Ben Bush did ship me the metal flasks, because they're round bottom flasks, and he'd checked the flasks. So he did some of the work, because he prepared the flasks and checked the flasks, made sure they didn't leak, and then he shipped them to me. But as far as the experiment goes, I did all the collection and running the experiment.
It's really like a double indemnity, because you have to not, you gotta first make sure you're having excess heat.
Right.
And then you gotta do this process to measure the helium. It's
Right.
like two huge efforts
Right.
in one.
Right. So the helium was measured back in Texas, University of Texas, and the guy that they worked with, I guess Ben had something to do with how they would measure the helium too. He worked with the mass spec guy, but he didn't run the mass spec. But they would, his method was pretty good. He would, they would, when they released the gas, they would go through a activated charcoal at a low temperature in some kind of ice bath, and so it would flow through this charcoal, and the deuterium, deuterium is about the same mass as helium-4. That's the problem. But the deuterium gas absorbs on the charcoal, but the helium doesn't. It's inert. So they would get separated, and the helium would go. Any helium would go through the mass spec, and the D2 gas would be left behind. So they worked out that, and that's the way the professionals that do helium-4 later found. They also have these kind of getters that hold up the deuterium and allow the helium to go on. The people that did this.
So he was able to measure this helium very accurately.
Right. Yeah. Yeah. I saw some of the results he brought him when he came to work for me. Eventually, you could see the peak on the the mass spec peak where the helium-4 was, and not only that, even though he didn't know which flasks were which, some didn't have excess heat, but it came out. I think all but at that time, all but one he got correct. If there's no heat, he found no helium. If there was heat, he did see helium. If there was a large amount of heat, he saw more helium. And there was less amount of heat, he saw less helium. So that all sort of seemed to correlate with what I'd reported on. I hadn't reported to him yet, but what I'd reported in my notebook.
So, at what point were you able to actually do that correlation with the heat and the helium production, matching it up to confirm that the fuel deuterium was converting to helium? At what point after that?
How do you mean confirm it?
Well, you're saying you got excess heat, and then you found the helium. Now you have to do some math to connect those things.
Right.
How did that come? How did you do that connection, that correlation?
Yeah. Well, at that time, okay. I think Van Bush tried to calibrate the mass spec because he got samples with filled with boil-off nitrogen, and he would let a little bit of air, measure a little bit of air into it, which would then contain a little bit of helium. And so he tried to do it by setting up some controls and kind of standardizing it so he would know how much helium they were seeing based on the size of the peak, based on some controls he had that contained nitrogen plus letting in a little bit of air. But I think he made a mistake on that because he came up with the fact that he could detect down to, I think, 8 times 10 to the 11th atoms of helium. And that'd be 80 parts. No, that's what's the part per billion?
That's 100 billion, right?
8 times
10 to
10
the
to 11th atoms.
11.
8 times 10 to 11th.
9's a billion, so
yeah.
100 billion.
Yeah, it'd be 100 billion, but compared to
800 billion.
Yeah, but compared to the amount of other gases in there, anyway, he thought that his detection limit was too low, is what it amounted to, because later we did more accurate measurements using metal flasks, and even Brian Oliver, who was the top helium expert in the country, he couldn't measure it that accurate. He could not detect that small amount. And so what we reported was a little bit off numerically, but it still correlated with when you had excess heat, you found helium, and when you had no excess heat, you did not see helium. And when you had larger amounts of excess heat, you saw larger amounts of helium. So that all pretty well fit.
Mm-hmm.
But the amount of atoms we reported, I think later we had to revise that because his calibration was somewhat off, I think.
Mm-hmm. Mm-hmm.
He was not better than the experts in the country. He could maybe get it close to what they were doing, but he wasn't better than what they were doing.
Well, that's a pretty difficult measurement. I mean,
Right.
measuring the number of atoms.
Right, yeah. Yeah.
Isn't it?
Yeah. Yeah.
You Parker, why don't you grab it? See who it is.
I know who it is. I'll call back who it is.
Oh, okay.
I saw who it was.
Oh. So when deuterium fuses to create helium-4, there's a approximate 24 MeV of energy created. That's true, right?
Right, yeah, 23.8.
And so were you able to then do that computation and get a number saying, oh yeah, we're close to 1-to-1 here with our heat?
Yeah. Later I did the calculation. From that number, you can calculate how many helium atoms you produce per second per watt of excess power, and that's you produced 2.3. I don't know if I got that written down in this report. Or somewhere 2.1 times 10 to the 11th atoms of helium per second per watt. That's if you're getting 1 watt of excess power, there's a known amount of helium-4 that's being produced if that's the only reaction. Mm-hmm. And so, or roughly 10 to the 11th. Well, when later we did the calculations, all the values came out around 10 to the 10th to 10 to the 12th, right in between there. And not only were we seeing helium-4, but it was the right order of magnitude. Mm-hmm. And the better the helium-4 was measured, later we had this done by another study was by Brian Oliver, and he's able to measure very accurately the amount of helium. And in that case, I think that my average came very. I think I got 2 times 10 to the 11th, 2 times 10 to the 11th, and it's supposed to be 2.3, and then 5 times 10 to the 11th. So I got very close to that value. And the most accurate helium measurements came pretty close to that value.
Who's Brian Oliver, and how did he come into the picture?
Well, when he heard that we reported helium-4, he was the expert that had been hired by DOD, I guess, or somebody to look for helium-4 in palladium of all the different groups doing cold fusion. They thought if helium was formed, it would be trapped in the palladium. And if the fusion took place deep in the palladium, that would be true. But if it's near the surface, like Ed Storms thinks, and like I think it's probably the case, though not exactly like Ed Storms thinks, but I think it's near the surface, then most of the helium-4 escapes. And Talbot Chubb, their theory predicted that also. It would be found in the gas that comes off. And so Brian Oliver, he did studies on a lot of groups, but they didn't find very much helium in the palladium. And that's reported in the book that I have, the chapter in the book is his work. So he was the expert in the whole country of measuring helium-4 in cold fusion experiments. So he and a friend, a person who worked with him, came up to China Lake. They wanted to talk to us about our results and get involved in. I think he was skeptical. He's always been a skeptic. Even today, I think Mike McCurby knew him. He did some work with Mike McCurby, but I don't think he's convinced that any of this is correct. But he wanted us to cut up our palladium and send it to him and have it be analyzed for helium-4. The problem with that is we'd already ran a control study in light water. We'd already repolished the electrodes. And then we ran the control study that we reported helium-4. We had to have control, so we just studied H2O in January of 1992, just before the paper came out in March 1992. We did 6 controls, and we did helium measurements on those, and all 6 showed no helium. But we'd polished the surface off, so the surface was not there anymore. And then we ran light water experiment, and so it'd be hydrogen going in and hydrogen coming out. If any helium was in there, it would have probably got flushed out anyway when the hydrogen comes back out. But they still wanted to analyze those rods, and I was kind of against it because these were my key rods. They produced excess heat in every experiment.
Yeah, why would you want to send them, you know?
But Ben Bush had sort of plowed ahead and did it on his own. He cut them up, and that was the end of those rods. He later worked with Mike McCruby. He was a type that he would want to do things his way, and he would do it no matter what you told him. You could not control him. That's why Mike McCruby never hired him, even though he spent a year or two at SRI. He never got hired. McCruby told me he just couldn't control what he did. He wanted to do what he thought was right and nothing else. So anyway, that's the end of those rods that produced over and over again excess heat.
So after those rods were gone, what'd you do next?
We tried other things. We tried segments off that same sample, and even off the same sample, they didn't produce excess heat. And other people tell me if you take a wire or a rod, one section can be different than another section. They're not. It's not uniform as far as being active for cold fusion, even on the same rod. So I've still got part of that rod left. Though it's probably worth quite a bit of money. I don't know that I should have it. Worth some money.
Let's hook it up.
Yeah. But in case I ever did anything else, I didn't want to just leave it there at the lab, and I wanted to have control over it. But I guess I could get in trouble. So. But anyway, anyway, these people at Rockville, Brian Oliver, he reported in his book chapter that he did not find helium-4 in my samples. And,
now, I think it was, I'm not sure, was it Peter Hagelstein who suggested that, well, when the helium is produced near the surface, maybe half of the helium goes into the metal and then half of it goes out. Is that what you were able to find? Like you were really only finding half of the helium in the gases? Or you found the full amount of helium and correlated it with the full amount of heat?
It seems pretty close to the full amount. And that's what my McCruby later found also. So I don't know. There's supposedly a recoil where part goes one way and part goes the other way, but I don't know if I quite understand how that would be.
Does helium want to be inside of a metal and trapped in a metal, or does it naturally occur that way?
A little bit can get in the metal by atmospheric diffusion, but it gets trapped. It doesn't, unlike deuterium, it doesn't diffuse through the metal. It gets trapped and gets stuck in the metal. And that's why metal flasks is good. It prevents atmospheric helium from getting in, because helium does not diffuse through metal. It might go a short distance and get trapped, but it doesn't penetrate through the metal.
It'll just sit there.
Right, yeah. It might sit on the outer layers, outer surface. It might be on the surface, but that's about as far as it would go.
So the fact that you were able to capture this helium and show that the production of helium is correlated with the amount of heat really suggests that the reaction is at or near the surface.
Right.
That was another conclusion that you could make.
Yeah, that's the conclusion. If helium is comes off in the gas, then it must be the reaction must be near the surface.
Mm-hmm. Mm-hmm.
And so if it's deep in the metal, Brian Alder would have found helium in more of the samples that he analyzed. It's interesting that he did find more helium in the samples from Fleischmann and Pons, significantly more than from other groups. But most groups he didn't find anything significant. Bockris, he did find at least one sample gave a high amount of helium-4.
Inside the metal.
Inside the metal. In the last years of Bockris's life, he'd been talking to Steve Crivet a lot, I guess, and Steve Crivet doesn't think it's fusion to start with. I don't think he thinks helium-4 forms, or it'd have to be by the Whittem-Larsen theory doesn't give you a good pathway to helium-4, I don't think. And so he was, anyways, for the last 2 years of Bockris's life, he was writing me all the time, he wanted to retract his report of helium-4. He has a paper that calls something about massive amounts of tritium and helium in an experiment. And it's probably in Ed Storm's book, it's probably cited there.
And Crivet wanted Bockris to retract this.
Well, Bockris wanted to retract it, and McCoubrey and I suspect Crivet was behind it. And Crivet was communicating a lot with Bockris. Bockris got, in the last year or two, you could see that he was not thinking clearly as he used to, you know. Of course, he reached 90 years old, and the year he died, in January of that year, he turned 90.
And yet he was one of the top electrochemists in the world,
he
right?
Was. Yeah, exactly. And he was very positive. His tritium was a big plus for this field for early on. And of course, he got severely attacked by the book by Gary Taubes. And it was an article published by Taubes in Science magazine, I think. It was they claimed this grad student had been spiking the experiment with the tritium. Yeah. Right.
Well, after you found this helium correlation, and you announced that in the Italy, ICCF in Italy, is that what you?
Right, the second conference.
The second conference.
Como, Italy.
Who was the next person then that said, "Oh, I'm going to try that. Let me do that too"? Who then confirmed what you did?
Probably an Italian scientist was probably the first that I remember confirming that. And then at the third conference in Japan, Yamaguchi claimed he saw helium-4. But that was kind of a flash in the pan. He never did anything further with it. He later went to work with Fleischmann and Pons, and Fleischmann told me one time he just came there to have a good time. He didn't really come there to work. So Fleischmann wasn't very impressed with him. But in the third conference, he did report a helium-4. And then this guy that I thought did some really good work early on was this Italian. I wish I could remember his name.
Cirillo?
It would take probably too long to find it in here, but I find Ed Storms has if he.
That might not be the one.
Oh yeah, in this other book, he discusses helium-4 and people who worked with it. You got his other book?
I'm not here. I should be able to find that.
Yeah, the section on helium-4, that's one thing I like about Storms. He does, I don't always agree with him. It's good that he's done what he's been doing. It's not all in one place, though. She likes to take her food and
She wants a view. A window seat.
Here he talks about my work and Bush. Okay, successful studies were performed in Italy and reported by Gozzi, G-O-Z-Z-I. Now, from what I can tell, he was a very good researcher, and he. So I would think he was probably second, and maybe Yamaguchi after that.
Mm-hmm.
And he gives a lot of references to Gozzi.
And these guys, was he able to then also capture all the helium that and correlate that with the heat? Or was that just, oh, we're seeing helium?
I don't think he did calorimetry, but I remember. But he
Okay.
was just measuring helium.
Okay.
You know, he did a lot of things, looking for products and radiation and so on. But that would take too much time to look all that up. But,
Yeah.
but Gozzi impressed me as a very good worker in this field, in early report of helium-4. In fact, right after my name in this book, Ed Strauss mentions his name, and that where it discusses my work, follows up with that.
Now, Michael McCubre was also able to reproduce this helium heat correlation.
Yeah, he did it probably even more accurate than I did. And he found that if he flushes what maybe is stuck in the metal or in the cell, he was able to get pretty close to the 24, 23.8. It was always a little bit on the high side, but that's because you probably don't get all the helium out, or else there might be other things going on. It may not be the only reaction. If there's something else going on too, the value will be a little on the high side. So that's the side where you would be the direction of the air is like tritium is going on as well.
Did you work with him on that helium measurement at all, or that was just completely independent?
Well, Ben Bush left my lab, and he went to work with Mike McCubre, and his job there was to find helium-4. But you know, Ben Bush, like I said, was kind of did his own thing, and he never got very much excess heat while he was working with me. For some reason, his experiments never worked out. And after these electrodes were destroyed, I didn't find anything. I went a whole year without seeing anything after those electrodes were gone. But we kept trying, but we had zero. You know, heat in equals heat out equals heat in for about a year, and it was hard to find anything else that would work. And,
so that was all through, 92 into 93 at that point.
Right, yeah, right. But then Ben Bush goes to SRI, and that's where Mike McCubre got involved in helium-4.
So he did his like 93, 94 or something like that.
But most of what McCubre did came after Ben Bush had left there, though.
Okay.
Ben Bush got an early report of a very small excess heat and a very small amount of helium. I think it was borderline because it was so small, like 10 milliwatts. I don't know how accurate you could measure that, and then a little bit of helium showing up. But Ben Bush said that he saved McCubre's program. That's what he told me by finding that result.
Where's Ben Bush now? Is he still active?
Nobody knows. He went back after McCubre. Went back to Legowski, worked for Legowski at the University of Texas. You know, he kind of ran labs for Legowski and kind of a senior postdoc. And they got some money for cold fusion, did some studies, and they got some money from Tom Passel's the electric EPRI money, and did some work, and then that ended. And when they had the American Physical Society had a meeting in Austin, I went to, and at that time I was at Bates College teaching. That would have been 2003, March 2003. the March meeting is what we usually had our APS meeting arranged by Scott Chubb, and that was March 2003. And I wrote Penn Bush, and he came to that meeting, and later he showed me his lab, and they didn't have any funding, so he hadn't had anything going on. And to pay his rent and everything, he was working in an electronics place, electronic factory. And I tracked him down about 4 or 5 years ago, finally able to get a letter to him. He's I think he's paranoid myself. He's become paranoid, and because he sent me a letter back, had no return address. He said that he warned me there are people out to get us. I mean, does that kind of make you wonder?
Yeah.
No return address, no telephone number, no way I could contact him back. Kind of warning me.
He's off grid.
You know. So I haven't been able to contact him since. But I mean, he was capable. Ben Bush was very capable, but he was strange. He was never married. I thought he would be a young postdoc, but he was already in his 30s when he came to work for me, you know. And he had this old car that he kept fixing up. He drove awesome. Most people wouldn't be driving a car that old, but he keeps fixing it up. And I remember when he flew into the airport and got a rental car, he was telling me how he was surprised at how these belts come in around him when he gets in the car, you know. The safety belts automatically kind of, he'd never seen that before.
Wow.
Yeah.
So after you had, you find this heat and helium, and you get confirmations over the next 2 years from others, that's when the ONR started giving you funding.
Yeah, after.
You think that helium result really was what?
Yeah. I reported the helium result at ICCF2 in Como, Italy. A very pretty place, by the way. Right on the lake that goes up against the Alps. You know, short drive to the Alps, short drive to Switzerland, 20, 30 miles up the road, and you're in Switzerland. This big lake at the foot of the Alps. If you ever get a chance to go, it's not too far from Milan, in northern Italy, but a really nice place for a conference, and that was one of the best conferences ever, I think, because a lot of key things happened there. And it's usually cited that McCruby showed the effect of loading, that's important. I showed that heat and force is a product. Stan Spock showed the co-deposition is another way to do it. So I think those were 3 key things that came out of the Como, Italy meeting. One of the best, I think, ever. But then the news media didn't care about us anymore. No news media there. It was in the Italian newspapers a little bit, like the word in Italian was fusione fredda or something. That means cold, I guess.
Yeah.
Do you know Italian or?
No, but I know those 2 words.
Yeah, right. Yeah, right. You know, so that's what started the Navy program, because here Bob Nowak had some key results from several people working with the funding from him, Stan Spock and myself, and also prior to that, a postdoc at NRL had reported energetic charged particles. I can't think of his name either. He didn't get his job there, but he reported measuring tritons or something to charged particles from a cold fusion experiment very early on. So that the NRL had made some contribution by that work. And I'm surprised he never wound up working there. I guess he was a postdoc and never got hired on.
So everybody got funding after that.
Right. So then there's about $1 million a year program that we had to keep secret. We couldn't call it cold fusion. The program was called Anomalous Effects in Deuterated Materials. That was the word for it, not cold fusion. And we were just investigating deuterated materials. And I guess of that $1 million, I usually got enough to cover me full time, maybe $200,000, but half of it goes to China Lake, you know. and they were overhead, and so I had full-time funding from several years, about 3 years.
What did you accomplish during those 3 years of funding? What was the big thing? Because you've already, you've got excess heat and you've been able to correlate the heat with the helium production. What did you do after that when you had that funding?
A lot of the critics were saying, well, what I measured was the helium diffusion through the glass. Helium can diffuse through glass, and you can measure it, and I did later measure it, and to reach the detection limit, it would have taken 20, 30 days or so to even reach the detection limit that I'd reported, and so it was not a factor. But we did measure. Brian Oliver did that, by the way, and another person. 2 different labs did it. We found another lab in Amarillo, Texas, that did helium analysis also. It was a Department of Interior laboratory. The person was expert on measuring helium-4, and then Brian Oliver was another expert, so had both those people measured diffusion of helium through glass, and they both came up with somewhat similar numbers. My hypothesis I presented at Como, because I knew what the criticism would be. I said, yes, helium can diffuse through glass, but you got all that deuterium, which is a small molecule also, and it can also diffuse through glass, and it's going the opposite direction. It's going to flush it, retard the helium coming in. You have a much higher concentration of D2 gas inside the flask that's diffusing through the glass. Even though it doesn't diffuse as well as helium, it still diffuses, and as it goes one way, and the helium's trying to come the other way. And if they're using the same sites to diffuse, it'll tend to retard it. And some people thought that was correct, some people didn't. Nobody knew for sure. But the measurements we did, we showed that with nitrogen, it diffuses, a flask filled with nitrogen, you get helium diffusion 2 or 3 times faster than is filled with deuterium and oxygen. So I did show that there's a factor of about 3 difference in the diffusion if you have deuterium in the flask than if you have some other gas like nitrogen that doesn't diffuse.
Mm-hmm.
So that's one thing we showed. And then we went to metal flasks, and we got excess heat again eventually, and we sent off samples to Amarillo, Texas, and he could measure in parts per billion. He was pretty accurate, plus or minus 1 part per billion. And we were getting, when we had excess heat, we were getting like 9 or 10 parts per billion. And when we didn't have any helium, any excess heat, we'd getting a lower amount, like 3 or 4 parts per billion. It was because a little bit of helium we did find does get in through a section of rubber tubing that we had there, not through the glass necessarily, but through some rubber tubing. So we had a background that was not quite 0, but every time we had excess heat, we were up above that, significantly above that, using metal flasks. So we repeated what we did before, but with metal flasks.
So the first thing you really did with this funding was confirm your results and even make them stronger.
Right, yeah, right. Yeah, because they couldn't criticize the use of metal flasks. And we also measured the background. So then I could start doing calculations where I subtracted the background from what was reported. If 9 were reported, I subtracted the background, and based on the excess heat, I could calculate the rate of helium-4 production per second based on per watt, and I would getting good values within experimental error what I would expect. And there's some points there I thought, I can just take the helium-4 values and use that for calorimetry. When I have higher helium-4, I have more excess heat. You could also relate the helium-4 report to the amount of excess heat that was present. And the people in Italy later thought of doing that as well. So you measure helium-4 accurate enough that that can be used as a measure of calorimetry, how much heat you're getting. Just going backwards from helium-4 to excess heat.
Once it's correlated, you're good to go.
Right.
Either way.
Right. Yeah. I thought it seemed to work out fairly well. I could take what they gave me for helium-4, and I could figure out what the excess heat should have been, and I was pretty close to that excess heat.
Would you say that you did that just to satisfy the critics? That you were compelled to quiet them And with this work?
Well, not the critics, I wanted more proof for myself as well. You know, I wanted to have a stronger case, and I thought that would build a stronger case. The only regret I had is I could never get ecstasy quite as large as I had got before with the glass flask. So the problem was getting a large ecstasy. I thought if I could really get 400, 500 milliwatts of ecstasy, then I could really pin this down exactly. But you know, I was getting more like 100 milliwatts or 200 milliwatts, and I would like to see 1 watt, you know, even 1 watt of ecstasy, and then a high amount of helium being reported, and you could relate it to the reaction with a lot more accuracy that way. But I was limited by the amount of ecstasy that I could get. But during this period also, NRL's part of the program was to make Navy materials, and we knew the material was the key. Some materials worked, some didn't. We thought if we could find a way to make in-house Navy materials to produce the effect, and then we wouldn't have to rely on outside sources that can vary. And so Dr. Imam, who is a good friend of mine, he's also Muslim, one of the few Muslims I really like. So I don't mind Muslim, but he's really a good example of a Muslim. I'm concerned about the radical Muslims that think their religion tells them to kill people. But his wife is a medical doctor. I've been in his home, and at that time that was probably grown out. He had 2 nice kids there. We had a nice visit at his home, and I always considered him a good friend.
And he's at NRL.
He just recently, last month or 2, he retired from NRL and has gone to work at George Washington University, where Dave Nagel is. I think they're going to collaborate some there. But he just barely retired and got a job at George Washington. I'm sure Dave Nagel helped him get that job, probably. But you want a good example for Muslim, he's one. You know, we'd go to these meetings in Washington, D.C., and you'd go out and eat dinner, and afterwards everybody was drinking, and Dr. Imam and I were the only 2. He kind of liked that. I didn't drink either, you know. And that was part of his religion as well. You know, right, everybody else was boozing it up.
So Dr. Imam shows up with, and what does he do with your? Yeah,
he started making different materials. He made palladium materials.
He would
send them to me, and we'd run them, and that's when we went a year without seeing anything, because we were running NRL materials. He made palladium silver for me, and I ran it, nothing, and various palladium materials, nothing. And he sent some.
Did he get depressed about that?
Yeah, you get frustrated.
And when did that end then? When did he give up? Say, hey, I'm not making anymore.
They finally had some meeting, I guess Scott Chubb and Talbot Chubb, they said they had a good discussion about this, and they said, we should try an alloy with boron, palladium and boron, with boron added. And they discussed how much boron to add, and they tried to make 3 different samples with 3 different amounts of boron. They were small, like 1 or 2% boron, but if you calculate by atom, boron is a very light atom, and palladium very heavy. Is still about 1 boron for every 12 palladium. Is, you know, the ratio of atoms is not too bad, 12 to 1 or 10 to 1. And they decided on these alloys to make with boron, and so Dr. Imam made those, and when he started sending me those, every one showed ecstasy, palladium boron. And Bob Nowak was excited. The program was getting kind of depressed then. We weren't getting good results.
Is this like 94 then?
Yeah, this was towards the end of 94, into early 95. I sent this one graph to Bob Nowak, and it shows it starting off near 0, and then it just kept going up and up and up, the ecstasy with that boron sample.
How do you think the Chubbs knew to try boron? What was it?
They were both deceased.
Did they tell you? Like, what made them think of boron?
They did tell me, but I don't know if can't remember exactly. But turned out to be a two-phase material. There's not just one phase. I mean, there's two structures of different type of structure, and it's a very unusual material in a lot of ways. It makes the palladium very hard. You know, it's very much harder than regular palladium, and it made it much slower to loading. It doesn't load as fast, and it's very slow deloading. Usually I could do studies of deloading by just taking it out and weighing it, and weighing it periodically over a period of several hours, and the weight would, all the deuterium would escape in a couple of hours. With the palladium boron, I had to stretch it out over a couple of weeks to get the weight, you know, all the deuterium to get back out, and the weight to get down to where it should be when it's gone. So instead of a few hours for deloading, it was weeks, several weeks to deload, and very much harder. And it's two phases, not one phase.
You mean alpha beta phase?
Yeah, there's two different phases of the palladium. The palladium boron has two different types of structures in it. You know, there's the alpha structure and there's the beta structure. It's not uniform, in other words.
So would you say that the palladium boron was a reproducible experiment then?
Yeah, I thought so. You know, the only one that didn't work, I did 8 experiments at Child Lake, and 7 out of 8 give ecstasy. The one that didn't work, in working this hard material, he had to make rods out of it. You know, he melts it under argon, and then he has to form it into rods, and it's kind of hard to form it into rods. It's so hard. You know, the one that didn't work in equation, it like a little bit folded over another layer, like it was a crack that was made by the swaging. So it kind of really had a built-in crack in it, which it tends to be an area where there's very little electrochemistry going on, and so the deuterium can get out, and the crack usually doesn't lead to good results. So 7 out of 8 gave good results. Then I took it with me to Japan when I worked at NHE, and in this book that's coming out, that's one of the main features is that graph of the palladium boron work. Martin Fleischmann did the analysis, and I did the analysis in Japan, and we pretty much agree. Well, I mean, not exactly on the values, but where the peaks are, where he shows peaks of excess power, I also, before he did his calculation, had the same peaks.
Over time?
Over time. Yeah, the excess power versus time. If you look at his graph and my graph is done in Japan, still in Japan, before I even left Japan, and
so they were basically the same size samples, same size electrodes, same type of cell design, and you got the same profile for the heat over time.
No, Martin just took the data from my experiment in Japan.
Oh.
And because it was off data acquisition.
Oh, okay.
But
I gotcha.
I wasn't sure I would get that data back from NHE. I didn't know whether I could trust them. So I took data every day by notebook, and I took it in the notebook during the working day, but all the time it was taking the data, printed data every 5 minutes. And it ran for about 70 days. Every 5 minutes is a data point. And when I got ready to leave Japan, they didn't give me the data. All I had was my notebook data. And I think they weren't, politically they didn't want to give it to me. They knew what I might do with it and give it to Martin Fleischmann. They didn't want to give data to Martin Fleischmann. But Dr. Sumi, or not, he was an engineer, wasn't doctor, but his last name is Sumi, S-U-M-I. When I got back, I emailed him and told him I really needed that data for my experiments. And he had already left NHE, but he had the data, so he sent it by email. And it was just coming in and coming in for an hour or two, you know. And I printed out, it's about a stack that high of all my experimental data. And I put it on a disc, and I gave it, of course Linda helped. I didn't know how to put it on a disc, but she did. And we sent a disc to Mike Mealy. I think he still has it somewhere. When we sent a disc to Martin Fleischmann. So Martin Fleischmann got all my data, And he went through it, and he did his analysis of it, like these equations, and it's better than what I do, but it comes out similar. So his analysis and my analysis show the same peaks, though we differ in the size somewhat. And so that convinced me that he's right, but he's better than me. Well, I knew he's better than me anyway, but anyway, he did his data. I took shortcuts and to make it as simplified, but he did it very exact. He used the complete data. He could track through the heating pulse and still use the data. I like to wait till the data, the temperature changed with time kind of leveled out. So that first term that I talked about yesterday was not a big term, because I wasn't sure how to evaluate that term anyway, so I wanted to make it small. I wasn't sure about the heat capacity of the system. Though they told me it was 490 joules per degree. Martin later found it was more like 450. That was an error right there in my data that I used their heat capacity that they gave me. But I didn't know how to measure it, so I had to use their data, what they told me. But and that led to the NRL report, Naval Research Laboratory report, and that'll be the figure presented in this book. This should be published soon. It's probably in print right now, but I haven't got a copy yet.
Let's take a break and maybe just take a little short walk. You wanna?
Right, okay.
I don't want to make you sit for so long, and it looks like Lady